Here we will look into the capacity of wireless channel. Now capacity indicates the maximum data rate that can be transmitted over the wireless channel with asymptotically small error probability, and also assuming that we have no constraints on delay or the complexity of the encoder and decoder. So basically the capacity implies how much amount of information that can be transmitted over the wireless channel reliably. And this is pioneered by Shannon, and this is based on the notion of mutual information between the input and output of the channel. And Shannon defined capacity as the mutual information maximized over all possible inputs. So when we talk about AWGN channel, so in AWGN channel we have the input xt discrete at time t, then we have addition of Gaussian noise, and we have output. So for AWGN channel we have yt is equal to xt plus nt, where nt is the Gaussian noise and xt is the transmitted information at time t. Then signal to noise ratio is given by gamma is equal to p by n naught b, where p is the transmitted power and n naught b is the power spectral density of noise. Then the capacity of this kind of channel, that is AWGN channel, is given by the Shannon formula. C is equal to b log to 1 plus gamma in bits per second. And this capacity for the time invariant AWGN channel depends on the mutual information between the random input X and random output Y. And this mutual information, what is this expression? We have seen it in our previous video on information theory. Mutual information is the relative distance between the joint distribution of X and Y and the product of the distribution of Px and Py. So basically it is the relative distance between Px comma Y and Px Py. And then using Bayes theorem, if we try to open this Px comma Y as P of X into P of Y by X, and if we try to substitute this in this expression, we get entropy of Y minus entropy in Y by X. And Shannon proved that the capacity is equal to the mutual information of the channel that is maximized over the input distribution. So this is the maximum capacity of the AWGN channel. If we send any data rate less than this capacity, so we can say the information can be transmitted reliably through this channel, and this is the maximum capacity that can be achieved. And Shannon also proved that there exists a code, for example like turbo code and etc., for which we can have the capacity, we can achieve this maximum amount of capacity through the AWGN channel. And we have seen that the input distribution that maximizes this mutual information is Gaussian. That means if we have this addition of noise here, we have y of t, then x of t. So we need to find out what is the distribution of xt that maximizes the mutual information between input and output when the noise is Gaussian. And we have seen that the input distribution is Gaussian distribution, and if the input is Gaussian, then we say the capacity or mutual information is maximum. And this results in capacity is equal to b log to 1 plus gamma. And since it does not consider any constraints on complexity and delay, this formula Shannon capacity C is equal to B log2 1 plus SNR bits per second is treated as an upper bound on the data rates. Now we have seen that the capacity of AWGN channel is given by C log2 1 plus SNR bits per second. And now in case of wireless channel, if we consider this X of T, and if we have a channel H, then we have the addition of NT, and we have an output Y. If we consider H to be time invariant, and then we have only one realization of the H over the channel because we have considered it to be time invariant. In this case, we can write capacity in form C is equal to log2 1 plus rho mod of H square, where rho is the long-term SNR and H mod of H square is the strength of the channel. And collectively this rho mod H square is called as the instantaneous SNR. And now there are two cases. First, we need to consider what is the behavior of this capacity in low SNR regions. In low SNR regions, if this is rho H square is X, then log 2 of 1 plus X can be reduced to approximately X log 2 E when X is small. That is for low SNR cases. In this case, the capacity is reduced to rho mod H square log 2 E. That means with SNR, it grows linearly. So in low SNR, capacity grows linearly with SNR, and when SNR is doubled, the capacity is doubled. So that means we can say for low SNR, we have a linear relationship between the capacity and the SNR. Whereas for high SNR scenarios, this log to 1 plus X is reduced to log 2 of X for large value of X. Then the capacity is equal to the summation of logs, that is the log 2 of rho and log 2 of mod of H square. So we see the graph of this log. This is SNR. So for low SNRs, we have seen that it is linearly increasing with the SNR. The capacity C is linearly increasing with the SNR. And for the high SNR scenario, there is a very small increase in the capacity, or we can say the capacity is increasing logarithmically with SNR, or we can say linear when SNR is defined in dB. So in case of high SNR, when we double the SNR value, when we double the rho to be 2 rho, then what we observe is that the capacity is only increased by 1 bit per second per hertz. Whereas on the other hand, in case of low SNR region, the capacity was doubling with respect to the SNR.